This video is about the chi-square goodness of fit test for multinomial probabilities. Sometimes we collect count data or frequencies in order to study how the counts are distributed among several categories or cells. Often, as we have discussed in previous modules, categorical data are used for making inferences about a population. In such instances, we may use an experiment called a multinomial experiment. A multinomial experiment is similar to a binomial experiment, but instead of two possible outcomes only, there are multiple possible outcomes for every trial or observation. In a multinomial experiment, we perform n identical trials with three possible outcomes for each trial. Each outcome has its own probability of occurrence, which is constant for all the trials. The sum of all the probabilities of all possible outcomes is 1. All the trials are independent, such that whatever outcome appears in one trial will not affect the results of the other trials. Finally, the results are observed frequencies of the number of trials that result in each of the k possible outcomes, which is denoted as f sub k. In goodness of fit tests for multinomial experiments, these observed frequencies for the k possible outcomes will be compared to their respective expected frequencies. The expected frequencies are computed by multiplying the total number of trials n to the probability for each outcome to get the expected frequencies per outcome. The goodness of fit test for multinomial probabilities requires a sufficiently large sample size. If all the expected values for all the possible outcomes of the multinomial experiment are at least 5, then the sample size can be considered large. If this is not met, the sample size may still be considered large enough if three other conditions are met. First, that all expected frequencies are at least 1, the number of categories or outcomes is at least 5, and the average of all expected frequencies is at least 5. The goodness of fit test for multinomial probabilities is a hypothesis test with the following hypotheses. The null hypothesis states the probabilities for each category or outcome, while the alternative hypothesis states that at least one of the probabilities differs from the probabilities stated in the null hypothesis. The test statistic is a chi-squared test statistic, which is computed using this formula. For each category or outcome, we get the square deviation of the observed frequency from the expected frequency and divide that by the expected frequency. The test statistic is the sum of all these values from each outcome or category. Like other hypothesis tests, we compare this test statistic to a critical value, which is a chi-squared value based on k-1 degrees of freedom, where k pertains to the number of groups or categories being compared. Now, this is a chi-squared value which we will obtain from another table called the chi-squared table. And this is how the chi-squared table looks like. So the organization of the table is very similar to our t-table. The graph here at the top shows that the chi-square value that the table gives us are chi-squares with a certain area to the right. And that area is the area that is written, or the value written in the subscript of that chi-square sign. So if you have here chi-square sub 0.995, then all these chi-squared values under this column have an area of 99.5% to the right. And the different rows pertain to the different possible values for the degrees of freedom, which is again k, or the number of groups being compared, minus 1. Now let's have an example for this test. In the microwave oven preference case, we are trying to see if the market shares in Cleveland mirror the market shares in Milwaukee. And we do that by comparing the observed frequencies in Milwaukee to the expected frequencies in Milwaukee, assuming that the market shares will be similar to the market shares in Cleveland. This case can be considered as a multinomial experiment with 4 outcomes or brands. Since we want to know if the market shares in Cleveland are applicable also to Milwaukee. The market shares in Cleveland will serve as the probabilities for each outcome or brand. Using the formula presented earlier, we compute for the expected frequencies for each of the four outcomes or brands. So that's 0.2 times the total of 400 or 80. Then 0.35 times the same total of 400 or 140, and so on. Afterwards, we compute for the test statistic using this formula. So that's the observed frequency minus the expected frequency, and the difference is squared, and divide that again by the same expected frequency. We do that for all the outcomes and get the sum, and we will get a test statistic of 8.7786. Now, this test statistic will be compared to a chi-square critical value based on degrees of freedom of 4 minus 1 or 3 at a certain level of alpha that we will identify. So if we use an alpha of 5%, so we can find that not in this page, but in the second page. So we have here the column of chi-squared values with areas all equal to 0.05, and we find its intersection with the correct DF, which is 3, and the chi-square critical value is 7.81473. Now this critical value is lower than the test statistic, or the test statistic is bigger than that critical value, and therefore we reject the null hypothesis at an alpha of 5%. And therefore we are 95% confident, or we have strong evidence to support the claim that these market shares in Cleveland do not apply to Milwaukee. Or in other words, at least one of these proportions is not equal to the stated proportions in the null hypothesis. So that's how we can interpret the results if we are able to reject the null hypothesis. Now let's have two other examples. We have here a contingency table of the political parties and positions of participants on a proposal to cut taxes. Using this dataset, let's answer the following questions. First, are the proportions equally distributed among all votes and parties? And are the proportions of being in favor of the proposal among the different parties equal? So first, for the first question, where are the proportions equally distributed among all votes and parties, we will use a goodness of fit test for multinomial probabilities, where the null hypothesis states that the proportion of Democrats in favor of the proposal, the proportion of Democrats opposed to the proposal, and all other four proportions are all equal to 1/6. So since there are 6 groups being compared and we want to know if they are all equal to each other, then we will all equate their proportions to 1/6. Now, to compute for the test statistic, we need to compute first for the expected frequencies, which is again the probability or the proportion stated in the null hypothesis multiplied to the total sample size. Since we have the same proportion for all the groups being compared, we multiply that to the total sample size of 404, and therefore all the expected frequencies will be equal to 202/3. And we use these values now to compute for the test statistic. So that's 85 minus 202/3 squared over 202/3. And then do that also for the 5 other groups and then get the sum, and we will get a test statistic of 85.3267. Now this test statistic will be compared to this critical value. So the critical value with an area of 5% to the right based on degrees of freedom of 6 minus 1 or 5. That's 11.0705, which is again something we can find here in the chi-square table. So the intersection of chi-squares of 0.05 and df of 5 is 11.0705. And since the test statistic exceeds this critical value, then we can reject the null hypothesis at an alpha of 5%, and therefore we are 95% confident that at least one of these proportions is not equal to 1/6. And therefore, we have strong evidence to support the claim that not all the proportions are equal to each other. Next, are the proportions of being in favor of the proposal among the different parties equal? To answer this problem, our null hypothesis should state that the proportion of Democrats in favor of the proposal and the proportion of Republicans also in favor of the proposal should be equal. But we need to identify the value of the proportions that we will equate these two. Unlike the previous problem where the proportion is clearly 1 over 6 because there were 6 intersections, the proportion that we will compare these two proportions to is not explicitly stated. And thus we have to get that from this contingency table. Since both are pertaining to the proportion of being in favor of the proposal, and 203 out of the 404 are in favor of the proposal, then those two proportions should be equated to 203 over 404. Thus, our null hypothesis should state that the proportion of Democrats in favor of the proposal and the proportion of Republicans also in favor of the proposal are both equal to 203 over 404. So we compute next for the expected frequencies for both groups, and again that's the same proportion multiplied to their respective sample sizes. So now the two are different. According to the contingency table, there's a total of 200 Democrats in the sample and 204 Republicans in the sample, and therefore we multiply 203 over 404 to different sample sizes. And therefore we will have two different expected frequencies. And we will use these two when computing for the test statistic. So that's 85 minus 10,150 over 101, and then get the square of that and divide that by this same expected frequency. And do that also for Republicans, and then get the sum, and we will get 4.7314. And we will compare this to this critical value for an alpha of 5% and degrees of freedom of 2 minus 1 or 1. And again, we get that here in this table, so that's this critical value. And since the test statistic is greater than the critical value, then at an alpha of 5%, we can also reject the null hypothesis. And therefore, we have strong evidence to support the claim that these two proportions are both not equal to 203 over 404. So at least one of them is not equal to 203 or 404, and we are 95% confident about that.